Okay, so what you see on this is binary code, and if you noticed in the video that we watched, everything comes down to ones and zeros. And I told you yesterday when we talked, when we were making the, you had to do the pictures, and they were using ones and zeros to make the squares black and white. That's what we're going to do today. But today we're going to not represent, we're not going to make pictures, we're going to make numbers. So what we're doing, binary code can be 4 bits, 5 bits, 6 bits, all the way up to 32 bits. Now, I'm not going up that high with you because, like she said, there's over 4 billion numbers you could make with that. That's way too high. We're going to stay down in like 4, 5, 6, 7, around that range. But they all work the same. So if you can do one, you can do any. So let me show you how this works. Like a 4 bits, you probably notice has 4 squares, right? 5 bits has 5 squares, and 6 bits has 6 squares, and so on. So if you did a 32 bit, it would have 32 squares. Now, the squares are going to be filled in black or left open. On your screen, they'll be white, or on your sheet of paper. Mine's yellow. I should have done a white paper, but they're either going to be filled in black or they're going to be white, left open. What we want to consider that to be is like off and on. Think about a light switch. So you want to think about if the light switch is on, it's light in the room, and so that number is going to be active. If it's dark, if that square is filled in black, then you want to consider like the light switch is off, and you can't count that square. It doesn't count because it's off, okay? So the only squares that count are the squares that are not filled in black, they're open, they're white, or in this case they're yellow on this sheet, but on your sheet they'll be white or black, okay? Now, every binary code, no matter how many bits, starts on the far right side. So on the far right side, that first square is always 1, no matter what. No matter if it's 4 bits, 5, 10 bits, it doesn't matter. So the first square is always going to represent 1. And it has to be the first square on the far right. It cannot start on the left. And I know that's backwards from what we normally do, but the code starts on the right side. Every square going to the left doubles. So if the first square represents 1, what does the second square represent? 2, because it's double 1. So the second squares represent 2. If you double that, what would the next square represent? 4. And if you double 4, 8. And then if you double 8, and then I'm going to double 16 and get 32. So a 4-bit code can go up to 8, 5-bit up to 16, and 6-bit up to 32, Okay? Now, the 4-bit code actually goes higher than 8. And 8 is the biggest number on the pieces, but if every one of those is open, turned on, then you add them together. You add the squares together. So if I were going to look at this 4-bit at the top, and I've got 8, 4, 2, and 1, if every one of those was turned on, you would add 8 plus 4 plus 2 plus 1, and you get 15. So the highest number that you could make with a 4-bit is 15. Okay? Now let's say, for example, let's say that I fill in one of these and make it dark. Well, that's not dark enough. No, that's not dark enough. Let's try this one. Oh yeah, that's a lot darker. Okay, so if I fill that one in and make it dark, that turns that one off. So that means only the 8, the 4, and the 1 would be on or active. So you would add 8 plus 4 plus 1 and get, what is 8 plus 4 plus 1? 8 plus 4 plus 1. That's not a trick question. No. 13. Okay, so once we do that, 8 plus 4 plus 1 would be 13. Ooh, that's way too big. Would be 13. Oops. Can't write. Okay, so do you see how that would work to add up the points? Okay, so let's do another example. And let's go down here and do maybe the 5-bit. Let's do an example there. If I were going to do the 5-bit, and let's say that I wanted to fill in, whoops, I didn't pick the right color. Imagine that's filled in. I know it's hard to see. So let's fill in, actually I'm going to make it bigger. I like it to be larger. Let's fill in that one. Let's fill in this one. And let's fill in this one. So what number would that represent?
20.
Right, you have the 16 and the 4 that's still on, so you can add 16 and 4 and get 20. Does that make sense how they did that? Okay, so let's go to our works. Do y'all understand at least how to do the binary code now? Okay, so